Hello, my name is Alexa Budol, and today I'm going to walk you through Lab 1 Constant Velocity from Physics 2211. The main goal of the lab was to record an object moving at a constant velocity without changing direction. The data was analyzed through the app Tracker, which recorded the experimental position versus time values. Using the experimental values, a computational model had to be built using an existing code which gave the predicted position versus time values, having that there were no external forces acting on the system. The two physics principles used in the lab are Newton's first and second law of motion. The first law of motion states that an object will remain at rest unless a force acts upon it, and that an object moves at a constant velocity unless a force is applied to the object. Newton's second law states that the acceleration depends on the external forces acting on the object, and inversely on mass. The initial conditions for the experimental values were recorded through Tracker. The initial position started from time 0, and the initial velocity was calculated by doing the change in position divided by the change in time of the first 2 points. Other additional conditions were recorded, such as the diameter and predicted mass of the object. The mass of the object was not that important in this experiment since the net force in the computational model was 0. This made the mass negligible and indicated constant velocity of the object for the duration of the computational model. In addition, the velocity and position update formulas were used to create the model. Here is a demonstration as to how the position and time data points were recorded through Tracker. The object used was a Mentos bottle, and as you can see in the video, the bottle moved at a constant horizontal velocity in the negative x-axis. Due to this fact, the graph that was recorded indicated a negative slope. On the right corner, you can see the graph generating on the negative slope and the data points being recorded on the table below. I chose to record the data from these frames because the bottle had already sped up and reached a certain constant velocity. To construct the computational model, the main things that had to be done were to update the initial conditions using the data from Tracker and integrate the velocity and position update formulas into the code. Here you can see that the initial position of the bottle was negative 0.00759 meters and the initial velocity was negative 0.506 meters per second. Also, here you can see that the mass was updated, but as said before, the F net is 0, so the mass of the bottle was negligible during the experiment, during the computational model. And in the while loop, I changed the time to be less than the final time in order for the data points of both the computational and experimental data to happen during the same time period. Also, here you can see that I changed the velocity and position update formulas, and they would be updated through each iteration of the while loop. Using the data obtained from the computational model and the experimental data, the following position versus time graph was created. The computational model line had a constant slope due to the fact that the net force was 0. On the other hand, the experimental line had certain curves indicating a change in velocity near the final time. This change in velocity could be due to the fact that there might be friction present and other external forces. Another reason as to why the curves can be seen might be that the bottle changed direction, causing there to be a shift in the velocity. Here are some additional questions related to the lab. What if instead of choosing the x-axis, the negative x-axis, the positive x-axis was used? If the positive x-axis were to be chosen, the main thing that would change would be that the slope would now be positive instead of negative. The velocities would remain the same, since the only thing that is changing is the horizontal direction of the object. Can you say how many forces were added together to get a zero net force? I wouldn't be able to say how many forces were acting on the Mentos bottle during the experiment because a lot of them can come into play. Also, we cannot say that in their experiment the net force was actually zero, because there were external forces such as friction, air resistance, and a main push from a person acting on the object. As you can see here on the graph, there are certain fluctuations, showing that the net force might not have been zero.